This is a short crash course on carburetors. Now this is not about specific carburetors, it's just about carburetor basics. You could probably write many books. You could write a book on just about every carburetor. Some books thin, some books thick. And so we're going to hit the highlights of how carburetors work, and you're probably going to see some surprises in here and stuff that you thought you knew but didn't. When I undertook this study from some material I got from Ford that was about 40 years old, these principles are still sound when you're working on carburetors even today. Now, the way a straw works on Earth, because you start with a small cavity in your mouth and you make it bigger, and the pressure from the atmosphere pushes down on the fluid that's in the glass and it comes into your mouth. That's basically, but on the moon, where there's no air pressure, you can't drink through a straw. That's just the way it is. Now the sea level pressure on Earth is 14.7 psi. There's no pressure in space. Altitude is where pressure decreases the higher you go. It's really interesting how that works. The air pressure at the top of Mount Everest is only about 5 psi. And you know, water boils at a lower temperature at those higher altitudes and everything else. But air pressure is everything. If you've ever driven a carbureted vehicle in the mountains, like if you go on a vacation trip and you start out at a place that's near sea level and you head up into higher altitudes, you'll be ashamed of the way your vehicle runs, because it runs terrible. So that's why for altitude modification you have to advance the timing and some other stuff. But long and the short of it is, here you are with the decrease in pressure at altitude, and that's important. Look at this. One of the things that's interesting here is 90% of the atmosphere is below here, and it's just really Mount Whitney, Mount Everest, and all that. So just look at those numbers. You can save these slides. Now, if you go by the 14.7 pounds per square inch and you work that out, you got 2,160 pounds of pressure per square foot. But everything is pressing together on all sides of everything all at the same time, including inside of our bodies. We got that same amount of pressure, and it's just totally balanced, right? So it's all. So if somebody, a person like me or you, wound up being ejected from a spacecraft, your body would just blow apart into little pieces, because you know, you see people floating around in space all in one piece and all that, but where there's a vacuum, your body's made to be on Earth where there's pressure, and if you're out there where you're in the vacuum, it just poof, it blows up. If you ever saw the movie Outland with Sean Connery, they actually showed you that in a place or two. Now pressure is predictable. That's one of the things about pressure. Here where we are, we can predict what pressure is going to do and what the lack of pressure is going to do. You got a vented gas tank and you're pumping gas out of it, it's going to do just fine as long as it can get air. But if you cap this thing off, it's going to cave that gas tank in if you keep pumping out of it. That's just the way it is. So the atmospheric pressure pressing in, if you reduce the pressure in this gas tank, which is basically a big square can, and in this case you're going to run into a situation where it caves it in. Well, the pressure being the same all the way around, you can predict what it's going to do. That's what makes helicopters fly, airplanes fly, and all that, because if it takes longer for the air to go above the wing than below it, the air is pushed downward by the underside of the wing, and you got lift. You got less pressure up here than you do here, and so that's why airplanes fly, basically. I'm not an aviation expert, but that's not hard to figure out, and birds' wings are made the same way. I don't know why it took so long for everybody to figure that out. They were trying to figure out how to fly. Alright, so, but whenever we make our lungs bigger, the atmosphere carries air into our lungs. And see, the pressure differential here, wherever low pressure is, in other words, say nature abhors a vacuum, it's going to try to fill the vacuum with air if it can. Now engines breathe too, you know, whenever you got your intake strokes pulling the air in, and because that piston comes down when that valve's open, see, it's creating low pressure in there and pulling it in, and then of course the high pressure here pushes it back out when that exhaust valve closes. That is not terribly hard to understand, but atmospheric pressure and pressure differential is what makes all that work. And so in the 1700s, Daniel Bernoulli knew how air would react when it was forced to flow through a restriction, and that was a long time ago. He also knew when airspeed increases, its pressure drops. And so if you got atmospheric pressure here, less than atmospheric pressure here, see what you got here is basically a Venturi. And so you basically are measuring atmospheric pressure right here. And so long and short of it, you study that slide, look at it if you want to, but I don't spend a lot of time on that. But multiple cylinder engines have continuous and overlapping piston movement. And so a steady low pressure is created in the intake manifold. So you've pretty much got a good solid vacuum in there if everything's working the way it's supposed to. Now if you got a problem with a valve or something like that, you know, you're going to have a bouncing vacuum in there. But a smooth running engine is going to have a nice steady even vacuum because the pistons are constantly working against that closed throttle plate at idle. Now the vacuum drops a little, but it tends to catch up with itself if the engine's not loaded. Now if the engine's loaded and you apply the throttle, the vacuum will go down and stay down. Kind of like you got a clogged up catalyst, right? And so you can use this vacuum to operate diaphragms if you're, you know, that's what they did for a long time. That's not done as much as it used to be. Most of every actuator on the engine is electrical now, but vacuum is still used for measurements, and they still use vacuum for doing things. Matter of fact, it was interesting to me how Duramax, whenever they first came out, were using vacuum solenoids to operate the EGR, which was very interesting. And they would use 2 vacuum solenoids the way Fords were using on some of their engines back in the mid-80s, you know. It works, I guess, you know, you do whatever you have to. Now, if you light a candle, cover it with glass, after a few minutes the candle goes out because it uses up the oxygen. Now the glass is full of air when you put it over it, but that air is all, the oxygen in that air is all used up, and you end up with inert stuff in there that you know, doesn't accelerate combustion. Alright, crude oil is a chemical soup. 2 basic chemical elements, hydrogen and oxygen, and over time they connect to each other to form hydrocarbon chains. Alright, and so you got 21% oxygen in the atmosphere, right? And so whenever you got this combustion that takes place, you get CO2, H2O, and CO. That's if it's perfect combustion. Now CO is carbon monoxide. That's typically from a mixture that's just a little bit too rich. If it's balanced, you won't get anything but these two. If it's a little balanced to the out of balance to the rich side, you're going to get CO. If it's bad out of balance, so that a lot of the fuel's not even burning, you're going to get hydrocarbons. I didn't put that in this diagram, but that's the way it works. Now, oxygen and gasoline's got to be mixed in exact amounts, or combustion will not happen. Now, I say that it will happen, but it's going to be dirty exhaust, or there's going to be like a lean exhaust is hot, and is, you know, it's really hot. That makes oxides of nitrogen. A rich exhaust is cooler, but it makes carbon monoxide and hydrocarbons. And furthermore, it also there's a lot of water being made too, you know, anyway, every time you burn the fuel. And if it's running too cool, a lot of that, your crankcase is going to get sludged up with the water and all that kind of stuff. But so here's your balance, 14.7. You notice the air pressure, see about 14.7 to 1. Look at that. This is there you go. 14.7 to 1 is also your stoichiometric balance for your fuel, and this is by weight. If you were going by volume, you burn 9,000 gallons of air for each gallon of fuel. But if you're going by weight, and that's how engineers measure fuel, whether you're talking about aircraft, injectors basically are measured by how many pounds per hour of fuel they can deliver. That's an engineering thing. We think gallons because that's how we buy it, you see. 18 to 1 is lean, you know, and then 12 to 1 is rich. and so you're basically going to have not enough fuel here in a really hot mix that's making oxides of nitrogen because your combustion chamber goes above 2500 whenever you're during the, the burn. And then rich is too black. I mean, it doesn't make black smoke unless you got hydrocarbons coming out of there. You don't see the carbon monoxide, you don't smell it, but it's there because you don't have a good clean burn. Anyway, that's a little graphic I put together. If you got liquid gasoline in a cup evaporating, it's got vapors rising, and a match is held over the cup, the gasoline doesn't burn. Only the vapor does, right? Matter of fact, you talk about people throwing a lit cigarette in a bucket of gas. It'll put the cigarette out, typically, unless the cigarette flames up on the way in there. In other words, if you throw it in the air that it's traveling through, causes it to burst into flame a little bit. But you can throw a lit cigarette into a little pail of gasoline. You can try that, and it'll put it out like water. But to get a more rapid burn rate, the fuel has got to be exposed to a bigger surface area. If an ounce of fuel is broken into fine droplets, and that's about gasoline direct injection does that, it's got droplets that are a whole lot smaller than carburetors or multi-point fuel injection, and that's one of the reasons that it's more efficient like it is. But each droplet is going to be surrounded by air when it's ignited and the explosion happens. But you got to have the droplets. The smaller the droplet, the better off you are. And if you could burn pure vapor, that's what you want to do. Mixture requirements vary with temperature and speed. You've got easy starting in cold weather. You need a rich mixture. As soon as the engine starts, it's got to lean out to prevent it from flooding and stalling. When an engine's flooded, it wets the spark plugs, and the spark plugs are actually the spark runs on that wet gasoline and never jumps across the gap, so it won't start if the plugs are soaked with gas, right? That's why when you mash the pedal all the way to the floor and put it in clear flood mode, it quits pumping gas in there, and that air coming in tends to dry those plugs off, and a lot of times you get one to start up that way. I used to stretch the spark at the coil wire to get one to start up, and then I let that spark stay stretched at the coil wire after it started until it burned all that junk off them plugs, and then I'd put the coil wire back in. Now sometimes I dodged a bullet and didn't have to pull the plugs and clean them for that reason. Now, the mixing of two ingredients occurs at the carburetor, your air and your fuel. Now there's many types and sizes of carburetors. They all function about the same principle. So you got atmosphere pushing down on the fuel in here, and you're making low pressure here, and that's going to cause this to go out of here. We'll talk a little more about that and how all this stuff works. I'm trying to make my way through this so I don't spend up too much of your time. The atmosphere above the fuel comes in through a vent. Now in reality, the vent is up in here. You might see that pipe sticking up through the carburetor that's got a angular cut on the top, and it's above the choke. All right, so that's going to let air go in this way. So you want filtered air. You don't really want it going through an open vent in the bowl. That's just really not a good idea because dirt and stuff gets in there and all that kind of thing. All right, so at the low pressure end of the main discharge tube, we can increase the Venturi effect by adding a smaller secondary Venturi, and it's suspended in the center of the airstream like that. See, so when this air goes through here, there's your choke plate, there's your throttle plate, and when the air goes through here, you're already creating low pressure here, and then you're doing it more intensely right here where you're wanting to pull the fuel out here. So if you take a straw, and sometimes you'll see this on a video or something, you take a drinking straw and you cut it in half, and you stick you got it sticking in the glass so that it's sticking out of the, and if you take that the part you cut off and you blow across the top of the straw that's sticking out of the water, you're going to see the low pressure you've created at the tip of that straw that's in the water start drawing that water out of there in a mist. That's a really good way to, basically, one of the basic principles of how a carburetor works anyway. There's a metering jet. This is really important. The size of that hole, I've actually had several different size jets in my toolbox. When I was working on Motorcraft 2150 carburetors, sometimes I would change the size of those jets to, combat little drivability problems and stuff like that. Now there's your choke plate, and the choke plate for cold enrichment, the throttle plate controls engine speed on the fly. That's the way that works. So basically this one right here, we'll talk a little bit more about that in a minute. There's your secondary Venturi, which is your booster, and your primary Venturi is built into the horn of the throttle body. and then there's your throttle plate. Okay. Now mist and vapor, you know, if you got a big old pan, it's going to put out lots of vapor. If you got just a glass of gas, you got a lot of gas, but you don't have much vapor because you don't have much surface area. So it's broken into little droplets by spraying. A large amount of surface area is exposed. So when you first spray this, like if you were spraying gasoline, this would be atomized, and because of the fact that it was atomized so fast, it would turn into vapor. And that's pretty much, you know, that's what your carburetor is trying to do anyway. You might notice that on some of the carburetors that will have the EGR, they'll have actually an early fuel evaporation thing. Some of the old Escorts had a little electric grid under the carburetor. On your General Motors cars, they would pipe the EGR across through into the intake manifold from one side to the other. They'd have a heat riser down there, and they want to warm that manifold up right under the carburetor, so it's going to vaporize that fuel. That's called EFE system, early fuel evaporation. And we don't ever think about that, but that's what an exhaust crossover is about, you know, where it's basically crossing over under the carburetor. Some of your old 390 Fords had a heater hose pipe running around the base of the carburetor for that same reason. And, you know, so anyway, that's for whatever it's worth. Atomization has got to occur before the fuel discharges into the airstream. And so you use a glass of liquid and a straw, you can demonstrate that principle of atmospheric pressure, and it can be used to, as I say here, if you just got vacuum, you're going to get pure, and you've had this happen before when you made a little crack in your straw by, you know, because it got kinked or something. Okay, you pull this, you got straight stuff. If you got an air hole in the straw, you're going to try to drink it, but air is going to mix in with it right here and go up. And so sometimes you'll have an air bleed where it's letting air come in from here, and if you've got a restriction at the bottom of the straw, you're basically going to get air bubbles, you know, atomization coming all the way up. I was really proud of these illustrations because I created them from scratch. You won't see these anywhere else. Now the liquid end of the straw is restricted to the limit of the amount of fuel flow into the straw. So lowering the air hole lets the air enter the straw beneath the surface of the liquid. Now the hole in the straw and the restriction at the end have got actual counterparts in a carburetor. So here's your main jet, that's your restriction, and here's your air bleed, see? So as it's pulling that fuel out of there, it's going to pull that fuel, it's going to turn into a sort of a mist, and then it's going to get pulled in here, and it's going to mix with more air, and it's going to turn into pure vapor by the time it comes out of there. So you got atomized fuel there. So low cranking speed means there's not enough airflow to draw fuel through the discharge line. So cold fuel doesn't vaporize as easy as warm fuel either. I talked about that previously. Okay, so if you close the choke, that's going to force that fuel to come out of there. You know, air bleed notwithstanding, it's going to force that, because it's kind of got that stopped up too. Of course, the air bleed, a lot of times it gets air from way up here. It'll have holes on the top of the carburetor, you know, that you don't realize what they were there for, but there they are. And so anyway, and there it is, atmospheric pressure pushing on this. I got that vent there for the purpose of illustration, but remember, it usually gets that vent from a tube that's coming down from here. All right, so now you got this automatic choke. See, to start with, we had to pull it. We basically, like on your lawnmower, you know, we had to pull the choke. And then as it started, we want to close that choke just as quick as we can. If you leave the choke pulled out, it kind of thins the oil, because gasoline from that rich mix goes by the rings and gets in the oil. Now, if we link the choke plate to a thermostatic bimetal spring, you know, basically the valve's going to change as the coil unwinds. So if you heat the coil up, it goes one way, and then if you cool it off, it goes the other way, and so it operates the choke for that reason. Okay, so that it basically, when it's cold, as soon as you tap the throttle, that choke is going to close. That's one of the things you had to know how to do, was to set the choke by tapping the throttle on when it had an automatic choke. And they either used exhaust heat, or they'd use a electric signal from the stator winding on the alternator. You might notice on some of the Chevy trucks, when the alternator quit putting out, there'd be an orange light on the dash. It would come on to say choke, because the choke actually gets its energy on a lot of them vehicles, while on the GM vehicle, like that from the alternator stator, which only has about 7 volts. And so they want it, the choke should be completely open within about 90 seconds if one's working right. Okay, there you got a choke pull off here. So when that thing shuts, the air going in is going to try to stop it. Going to try to pull it open, but that diaphragm is necessary. That choke pull off is supposed to open at about 1/8 of an inch. Now I used to see sometimes this would get weak, and the air that was coming in would be coming in too fast, and it would pull that choke open too far, and then that fast idle cam, which I'll talk about in a minute, would catch it, and then it would stall. But that spring's supposed to be strong enough to where this diaphragm that's hooked to manifold vacuum is supposed to automatically pull that open about 1/8 of an inch. Now there was an adjustment on these, and if they weren't set right, or if the diaphragm was busted, there would be issues. So anyway, so in addition to controlling the position of the choke plate, the thermostatic coil is linked to a cam down here on the bottom, the fast idle cam. And during the start procedure, the throttle's open, the cam rotates to the fast idle position, and that fast idle speed is necessary to make sure enough air and fuel is pushed in to keep it from cutting off. And that's something, this was developed over a long period of time. And like I say, there's tons and tons of different things you could say about carburetors. We're just hitting the highlights here. Alright, so you got your needle and seat. Everybody that's ever worked on a carburetor is familiar with those. This adjustment is really important because if that fuel level is too high, you can wind up with it beginning to siphon out here. See, if that fuel level has got to be below this point right here, and that's why the float level was so important. And that's why those carburetor kits that come with all those incredibly complex instructions tell you exactly how to set that. Some of these would be brass, soldered brass like a shell, and more of them, as time went on, became a sort of a black foamy thing. It was solid foam, but it would float, and it would close that needle off every time. Whenever it would come up, it would stop it. Kind of like a commode float. Whenever it comes up to where it's supposed to be, it maintained the level in that reservoir. Now, if you had a clogged up fuel filter and it couldn't get the fuel in there fast enough, and you were really getting on it, this would drink that fuel out of there fast enough to where you'd start losing power and stuff. That's when you notice it. A fuel filter, some people would say, well, my vehicle wouldn't start, maybe I'll change the fuel filter. Well, that's kind of silly, because the fuel filter, unless it's got a completely stopped up sock in the tank or something, is not going to keep it from starting, but it will cause you to lose power when you're trying to pass a car or something like that. Now during engine idle, the air fuel mixture has got to be supplied a different way past this idle mixture screw. You notice how it's pointed on the end? You can screw it in and out, and you can basically feather that thing so it's idling really, really smooth. If you've got two Venturis, which you're typically, even on a 4-barrel carburetor, 2 of them are going to be the ones you're going to be using unless you're really getting on it and you open the 4-barrel. But you're going to adjust both of those, right? When my dad used to work on those vehicles that had 2 carburetors on them, like Corvairs and some of the older Type 3 Volkswagens, he would listen to both of them with a hose, and then he would turn them adjust them with his fingers, and he would keep feathering both carburetors until he got it running real smooth. Well, that's what this is all about. The fuel that it's running off of, it's not coming from here when it's idling. It's actually coming through a set of passages and going by that idle mixture screw. Of course, it's going to get a little bit of air in there to mix with that, but whenever you turn that screw in and out, you're basically changing that, and that's what that idle mixture adjustment's all about. So you can look at that slide a little more too if you want to. Now the low speed systems fade out as the main metering system fades in, and the hole through the jet there's a metering orifice here, and you might see these metering rods now on your feedback carburetors that General Motors came out with on their computer command control in the early 80s. I mean real early 80s, like 1980 I think. I went to school on those in 81. But they actually connected a solenoid to this, and they would make it go up and down really, really fast, like 10 times a second. And how long it stayed down during each time it went down determined how it was regulating the fuel based on the oxygen sensor input. But and this right here, you can see if it's got this stepped rod, or sometimes it'll just be tapered, it won't be stepped. If it's deeper in there, it'll reduce the amount of fuel that's able to go out of that jet. And that's called a metering rod. And a lot of times it's hooked up, with this linkage, so that whenever you give it the gas, it raises this up out of here, and whenever you let off the gas, it comes back down because it doesn't need as much fuel. That's a mechanical metering system. Okay, so next slide. Now the vacuum metering system you might be familiar with. It'll have a vacuum diaphragm on there, and it's operating a little power. They call it a power valve, and this thing goes raises up whenever this vacuum drops off because of more engine load. This will raise up and let more fuel go through there. See, and so you've already got fuel going in here, but you get more fuel when that vacuum diaphragm lets more in there. And some of the carburetors even had two-stage power valves in them and all that. People call this a power valve, but it's a vacuum enrichment is what it is. And so that vacuum is hooked to that. Sometimes it'll have a hose connected to that. Sometimes it's directly connected, with a passage drilled or whatever. And so that's a little interesting cross section on how that works if you want to know about it. Now the accelerator pump, if you open the throttle really rapid, you're going to have to, this accelerator pump is going to force this. It's got a little weight, it's got a little ball, it forces that up and it squirts in there. I used to look whenever I had a no start on a carburetor vehicle. The first thing I'd do is I would take the top off of the breather and get to where I could get my hands on the throttle linkage, and I would watch those accelerator pump jets, with they look like little pipes, one squirting out into each Venturi, and I would hit that throttle. If I didn't see any fuel squirt out there, then I would know that the carburetor was dry on fuel, and you need to go find out why you're not getting any gas to the carburetor, if it was out or whatever. Now this thing right here, just the ball by itself isn't good enough, but that weight sitting on top of it, see, on the ones that were designed. Now the other thing, on some of this is a fairly common way of doing it. Some of your Fords had this right here. They had a little diaphragm, and it would actually operate the same way this does. So if you got this, you won't have this. And if you got this, you won't have that. It's going to be one or the other and all that. But the accelerator pump, well, if it's not working, it'll stumble, fall on its face. Also, that accelerator pump, when you're first starting and setting the choke, it squirts some gas in there and wets the manifold. Even on the fuel-injected engines, you still have this function because it double pulses the injectors when you're starting it cold. That's just the way it is. And so, get used to that notion. Also, its other components, you got barometric pressure compensation. That's on this thing. You got a dash pot right here that keeps it from coming back to idle too quickly when you're letting off, because if you do on some of them, it'll stall. Then you got this right here. You got a solenoid that's a throttle kicker. They also have hot idle compensators. Later ones had these little idle speed control motors. GM and Ford both used those. Then your spark advance is ported vacuum. Only had vacuum whenever you were giving it the gas. If you measured vacuum here whenever it was idling, you wouldn't see any. But when you go to crack the throttle, this would start delivering vacuum and pull the vacuum advance the time, and give you an extra zoom when you're taking off. Now this would be your throttle position potentiometer. This is an archaic picture of that. But this dash pot, even on the ones that have electronic throttle bodies, electronic idle speed control, they still have what's known as a dash pot function. Because whenever it'll stall if this thing doesn't let the idle come down. And if the newer one, if it doesn't know it's all the way at closed throttle, it'll hold the idle a little higher sometimes, and it'll be in that dash pot mode. And you'll say, why is my engine idling too fast? And if you look at your scan tool, it'll say part throttle. And then so if you've got to fool around with those wires, because there may be something going on there, and when it comes back to closed throttle, it'll release that dash pod function. I've actually seen vehicle speed sensors malfunction and cause it to stay in the dash pod function, but that was an isolated thing that I saw on one car. But okay, so you got idle tracking switch. You notice that switch right there? It's basically supposed to send a signal whenever you've let off the gas. That's built into your idle speed controls on your GMs and your Fords and all. Now, when an engine idles for an extended period of time, you might have seen these hot idle compensators, little bimetal strip in there, and it opens the passage when the vehicle gets hot. It says the heat generated makes excessive vaporization of fuel in the bowl, So it's going to open that valve to equalize that on some of them that have really hot. I've actually seen this on old late 70s Lincolns though, so this is not just vehicles with small, small vehicles with high temperature engine compartments. But that hot idle compensator is something that most mechanics don't ever think about. And I've actually seen those get damaged, and it'll cause it to run rough, because if that thing's open when it's not supposed to be, it'll make it idle rough and run lean and that kind of thing. Alright, I've kind of hit the highlights on this thing, and I wanted you guys to be able to whiz through this quick enough to where you didn't get bored for hours talking about this kind of carburetor and that kind of carburetor and 2 barrels and 4 barrels and all that kind of stuff. We can cover that later. Then there's variable Venturi carburetors. I've talked about those before. But one of my subscribers asked if I'd do something on carburetors, because a lot of the younger guys he worked with couldn't tune a carburetor, and there was a need to do that periodically. But I just wanted to touch on this and run through it, and that's my Monday presentation for today. Leave me a comment. Let me know if this did you any good, or if you learned something you didn't know. Hit a like, hit a subscribe, share the video, and I really appreciate you guys watching every week. We'll talk to you another time.